Hello everyone, welcome to Aeromechanology channel. Today's topic is sheet metal design guidelines. On material selection. Choose the appropriate material based on strength. High strength steel or aluminum for load bearing parts. Corrosion. Resistance. Stainless steel or coated metals for corrosion sensitive environments. Ductility. For parts requiring significant forming or bending. Cost. Balance between material cost and required performance. Two, sheet metal thickness. Use standardized thicknesses or gauge for ease of manufacturing and cost reduction. Common thicknesses are 1 mm, 1.5 mm, 2 mm, and so on. Avoid thickness variation within the same part to reduce complexity in forming and tooling. Bend radius. The minimum bend radius should be equal to or greater than the material thickness to prevent cracking or deformation. As a rule of thumb, bend radii should be at least 1 to 2 times the thickness of the material. Larger radii will reduce stress on the material and tooling. Bend relief. Use bend relief to avoid tearing or warping where bends meet edges or other bends. Relief can be slots, notches, or rounded corners to prevent material thinning or cracking. Ensure that bend relief is greater than the thickness of the material. K-factor and bend allowance. The K-factor represents the location of the neutral axis during bending, typically ranging from 0.3 to 0.5. Bend allowance accounts for the stretch of material along the bend, ensuring accurate flat patterns. Utilize accurate K-factor calculations based on material type and bend angles. Avoid overbending. Overbending leads to excess stress in the material. The design should minimize acute angles. Avoid bends less than 90 degrees whenever possible to ensure ease of manufacturing. Minimum flange length. Maintain a minimum flange length of at least 4 times the material thickness. Flanges shorter than this can result in manufacturing issues or distortion. Tolerances. Define realistic tolerances for sheet metal parts. General tolerances for formed features should be around plus or minus 0.5 mm or more, depending on part complexity. Critical dimensions may require tighter tolerances but should be minimized due to cost implications. Nine, hole sizes and placement. When it comes to hole diameters, the minimum hole diameter should be at least the material thickness. For the distance from the edge, holes should be placed at least 2 times the material thickness away from the nearest edge to prevent deformation during punching or cutting. And for hole spacing, the distance between holes should be at least 3 times the material thickness. 10. Tabs and slots. Design tabs and slots to aid in alignment during assembly. For tabs, keep the tab width at least 2 times the material thickness for strength. And for slots, ensure the slot length is at least 1.5 times the material thickness to avoid material distortion. 11. Embossing and louvers. Use embossing to increase strength or for features such as ribs or standoffs. Avoid excessive depth for embossed features, keeping them under 3 times the material thickness to maintain material integrity. For louvers, maintain standard sizes to ensure compatibility with tooling and prevent manufacturing complexity. Notches and cutouts. Avoid sharp internal corners for cutouts. Use a minimum radius, preferably at least half the material thickness, to avoid stress concentration. Notches should be placed far enough from bends to prevent material distortion. Fillets and corners. Avoid sharp internal corners in sheet metal parts. Use fillets or rounded corners with a radius of at least 1 times the material thickness. External corners should also be rounded to prevent injury and ease of handling. Hemming and seaming. Hems are used to strengthen edges and make them safer by folding the material back onto itself. Minimum hem length should be at least 4 times the material thickness for proper fabrication. Seams. Ensure seam overlap is adequate for joining, with proper alignment in assembly. Fastening and assembly. Self-clinching fasteners, like nuts and studs, are commonly used in sheet metal to provide strong attachment points. Riveting, welding, and screwing are commonly used joining methods. Ensure fastener holes and attachment points are designed with appropriate clearances for the selected hardware. Spring back occurs when the material tries to return to its original shape after bending. To compensate for spring back, apply over bend angles slightly to account for material recovery. Design bend tools, considering the material type and thickness. Laser cutting and punching guidelines. Avoid intricate shapes and small cuts that require high precision unless necessary. Common cut tolerances should be around plus or minus 0.1 millimeters for laser cutting. Optimize the cutting path to minimize heat effects and material distortion. For punching, avoid small, closely spaced holes, as they can distort the material. Design for manufacturability, or DFM, is crucial in creating efficient and cost-effective sheet metal designs. One key principle is to standardize features across designs. This helps in reducing the need for specialized tools, which can be quite expensive and time-consuming to produce. It's also important to minimize complex geometries. By doing so, you reduce the number of bends, cuts, and operations required, making the manufacturing process much simpler and more efficient. Another critical aspect is to design with tolerance stack up in mind. This means considering how small deviations in each part can add up and potentially cause complications during assembly. Proper planning can help avoid these issues. Lastly, nest parts efficiently on the sheet. This helps in reducing material waste, which not only saves costs but also supports sustainable manufacturing practices. By following these guidelines, you can ensure that your designs are not only functional but also optimized for manufacturability. 19. Minimize welding. Where possible, design parts to be joined mechanically rather than through welding, as welding can introduce heat distortion and increase production costs. If welding is necessary, provide ample access to the welding area and allow for welding tolerances. 20. Surface treatments. Consider surface finishing techniques like painting, powder coating, anodizing, or galvanizing to enhance appearance and prevent corrosion. Plan designs for coating compatibility, ensuring even coverage and allowing drainage for wet coatings. By following these sheet metal design guidelines, you can enhance the manufacturability, reduce costs, and improve the quality of your final product. It's crucial to balance functionality with manufacturability, always working closely with fabricators to ensure that your designs are practical and efficient. Thanks for watching. Please like, share, and subscribe. Happy learning.